Hello, today I'm going to be showing you the electrolysis of water. I'll show you the procedures first, and then we'll talk about kind of the theory behind it. So what I have set up here is a petri dish with deionized water. It also has some aqueous potassium nitrate, although you could use any soluble salt for this. We just need a little bit of an ionic compound to be able to conduct electricity well through it. I also have universal indicator in with the mixture, and universal indicator follows these colors just about. So it's going to help us see the change in pH as the electrolysis is running. So then what I'm going to do is I have a 9-volt battery with 2 alligator clips, and the alligator clips are attached to just pencil graphite. The graphite is a nice conductive material that doesn't interfere with the reaction. And then I'm going to insert the 2 graphite leads into 2 opposite sides, and we're going to let it run. You can already see a color change happening at the 2 different ends. And for reference, the yellow alligator clip is attached to the negative side of the 9-volt battery, and the red alligator clip is attached to the positive side of the 9-volt battery. And you can see that the negative lead is starting to turn like a dark purple, indicating a very high pH, and the positive terminal is starting to turn like a reddish orange color, indicating a much lower pH. Now, if you were able to zoom in really far, you'd be able to see there's bubbles forming. So one of these electrodes is producing oxygen gas, and the other one is producing hydrogen gas, because it's splitting water by adding that energy from the battery. All right, so what's going on here? These are the 2 half reactions that we have, and both of these are written as reduction potentials because the electrons are being gained. So these are our 2 reduction potentials. Now, in order for this to be an electrolytic cell requiring a power source, the E cell overall has to be negative. That's because of this equation, delta G equals negative NFE. And if we want delta G to be positive for a reaction requiring an input of free energy, that means the cell potential must be negative, because a negative times a negative will give us that positive delta G that we need. So in order to get a negative cell potential overall, I need to flip one of these reactions so that it's an oxidation reaction. And I want to flip the top one. That way both of our potentials are negative when we add them together. So I'll flip the top one. I have 2H2O, O2 plus 4H plus 4E negative, and that will now be, as an oxidation, negative 1.23 volts. Then if we write our overall, I'm going to add them together. The electrons are the same. So I have 6 waters breaking down to form hydrogen gas, 4 hydroxides, oxygen gas, and 4 hydrogen ions. And the overall cell potential will be negative 2.06 volts. Now, in reality, oops, I missed the H plus part. In reality, the 4OH and the 4H plus will probably interact, but since the 2 half reactions are happening on either side of the petri dish, until it starts to mix overall in the petri dish, you're going to see a difference on one side versus in the hydroxide ion concentration versus the hydrogen ion concentration. So this is our overall what's going on. Now, if we look at this a little bit more specifically, you can see that in this top half reaction, we're producing hydrogen gas at the same side that we're producing hydroxide ions. Those hydroxide ions indicate a higher pH, and what's happening here is it's still reduction because it's gaining electrons, and reduction always happens at the cathode. And if you look back at the procedure, the side that was increasing in pH was attached to the negative terminal of the 9-volt battery. Now let's look at our other half reaction. This one is our oxidation half reaction because it's losing electrons and it's producing hydrogen ions. That means that the pH is decreasing. And so anytime you have the oxidation, we call that the anode. So at our anode, the pH is getting lower, and we saw that red color appearing at the side that was connected to our positive terminal of the battery. So this is showing us kind of what's happening in terms of an electrolytic cell, and specifically the electrolysis of water. AP students do not need to know the positive or negative labels for electrolytic or voltaic cells, but they should be able to identify reduction is at the cathode, oxidation is at the anode. And they should know the difference in cell potential for an electrolytic versus a voltaic. Voltaic has to be positive instead.